Supervisor Christina Pepper. Okay, so we all know that each, like in the ground, we have different receivers. And aircraft, they broadcasted their information, which is okay, obvious for everyone here. And the point is, if the messages are received or broadcasted from the aircraft, not all of them are received by the sensors. Okay, so as an example here, some of these messages are received, and some of them they are not received. And some of them they are received by more than one sensor, 2 or 3 sensors. So, okay. So we can know that from this picture that some of the coverage area or the boundary for the sensors are interlapping. So we have intersection area between the receivers. So we were thinking about using this like idea for a new method to predict if the message has been modified or not. So the problem is, if we have a source and the destination, and the aircraft is like going from source to destination, crossing the different type of sensors. As an example, in this figure, it goes from like through sensor number 1 and sensor number 2. But the point is, or the problem, if we have an attacker, and this attacker would like to spoof or to change the location information inside the ADSB message, because the main feature behind the ADSB messages, like it's sent or broadcasted in a plain text, so there is no encryption, nor decryption. So we have 2 types of attacks. The first one is a random drifter attacker. Attacker, he doesn't know anything about our methodology. He would like just to spoof the location in a random way. So he just like put the red dots here to spoof the location. And the most like a smarter attacker, which is targeted precise drifter attacker, he's slowly changed the position of the aircraft in a way that he tried to mimic us like he's a legitimate aircraft, but by the time he tried to avoid the legitimate trajectory and go to somewhere else, like another destination. So how to check the trustworthiness of the received messages? By doing like comparing the received ADSB message from ADSB messages from OpenSky as an example, with the computed or expected location. For sure, this is not new. And there are a lot of existing solutions trying to deal with this cross-check for the location verification. Multi-iteration is a very famous methodology that is being used for a long while time. And it's based on like the message should be received by at least 4 receivers on the ground. But, okay, I'll come to the challenges, okay. And also there is also another method which is called lightweight location verification. It's like using the 2D grid. And also our method MapPro, it's like based on the anchor points. So we have to have trusted anchors, and then based on these trust anchors, we could build and predict the next like messages and predict if they are identical or like if they come from legitimate aircraft or not. But the point is, with multilateration, it requires 4 receivers to receive the message, which is like not applicable for the whole messages that are broadcasted from the aircrafts. And based on our knowledge, like 30% from the whole packet only received by 4 sensors. So lightweight location verification comes to handle this issue and to like verify the message that are received by 2 sensors and so on. So, but the problem is with the grid size. MapPro comes to verify the trustworthiness of messages that are received by 1 sensor, but as I said, we cannot use it for the whole trajectory. Only part of the trajectory we could use it because it's like based on a trusted anchors at the beginning. So what is the system methodology that we are trying to bring up as a new method to verify or to check the trustworthiness of the messages? As I said, like there are different sensors, and these sensors, they are overlap between each other. So as an example, in this figure, there's an aircraft, and this aircraft crossing an area that's covered by 3 sensors. So we were trying to get or predict the location in this intersection area. So once we have this intersection area, we could predict where is the aircraft inside this intersection area. If we have like more number of receivers, means like the intersection area, it will be smaller, means also the accuracy, it will be the prediction of the expected location, it will be much more. So this is the, before like doing the experiment, this is the assumption. If we have more receivers, we have a smaller intersection area, then we have more accuracy. So we tried two like methods at the beginning, and this is the first method is to get the central point inside the intersection area. But the problem with this method, if we go like the intersection area is very large, this does not make sense, right? If you are predicting the central point inside this intersection area, and if the two sensors, they are locating beside to each other, this means we are in just taking only the central point of the same sensor as, because they are locating near to each other. Plus, if we take another issue with this problem, if there's a aircraft going from source S to destination D, and crossing like sensor at the time 1, sensor number 3 and 5. So the prediction could be the central point between the two intersection area of the coverage of these two sensors, and this could be this in the middle. But if that at time 2, the message also received by the same set of sensors, this means that we'll take also the central point, but the aircraft is moving, so this is not correct. So the aircraft is moving, but we are getting the same prediction all the time. So we're thinking about another method, which is like, for inside the intersection area, create a mesh network, and then generate a random point inside this intersection area. And based on the distance from this point to the first sensor that will receive this message, we'll get a weight. So we first order them based on time of arrival, and then we take the distance, and then we give them a weight, and then pick the one that is closer to the sensor that received this message. But also we have a problem with this. Which one to pick, actually? If we assume in this scenario that if the message is received by sensor number 3 and 5, then this is like, okay. And then at time 2, it's received by 5 and 3. We're still receiving the same, like, okay. At the first time, it's received by the sensor or the point that is closer to sensor number 3, but in the second time, it could be received by sensor number 5. 5. And then at time 3, it comes again, it's received by sensor number 3 and 5. So picking the best value inside this mesh network it could be like very accurate and should be high or consider different criteria to be more accurate and more precise. So what are the questions that we are trying to deal with? First of all, we are trying to location prediction. So it should be smaller. As I said, smaller is better. The intersection area between the coverage sensors. And also the accuracy for the prediction should be high. Once we have a very high prediction, then we could use it for detecting the attacks. Plus how this like accuracy prediction and accuracy depends on the sensor or ADS-B sensors. So we observed that the density, location, and coverage of the on-ground sensors affect on the prediction accuracy of the prediction of location of ADS-B messages. So how we could improve the accuracy involving the time, also sequence pattern, receive signal strength. So we have to think about different parameters also to involve in the like prediction method to make the accuracy of prediction much higher, and then use this prediction to detect if there is an attack. So regarding the sensors, how the sensors location affect in our methodology. So if they, as I said, if they are sparse enough, then this means that we could use them and we get more higher accuracy. If they very dense to each other, this means they are considering as one sensor. So we don't take that advantage of like receiving the message by multiple sensors. How's the coverage for the sensors? We observed like some of the sensors, they have small coverage, some of them they have huge coverage. Maybe one aircraft could cross like from the source to destination, and these messages that are like broadcasted by this aircraft received by the same sensor for the whole trajectory. Also, the number of sensors. So how the number of sensors affect in the accuracy of a prediction. For evaluation, we use like for one data, 2 million ADS-B messages, and we got from this 1,661 flights or trajectory, and we were getting 45 sensors. I used like all data from OpenSky because at the beginning when we asked for the location for the sensors, it was so critical to get the location because it's sensitive information. So we just play with the old data from OpenSky, and for the area that we are targeting, we just only got like 45 sensors, and we use the location for these 45 sensors. So first of all, we try to get the coverage for the sensors that we have. And this is the number of the sensors and the coverage. We observed that from the experiment, there are some locations that, okay, each sensor receives some messages from different locations. This could be considered as an outlier, so we don't need them. So, and this could affect it in our accuracy. So first of all, we remove them, and then we got the ones that without these outliers to make the accuracy for the prediction much higher. Plus, because the information of location is very sensitive, we try to see how we could like predict the location of sensor at first, and then try to compare it with the original one. So from these images, we can see how is the predicted one and the computed one, the actual location of the sensor from ADSB. Some of them, they are close, some of them, they are far away. I believe that if we use 1 week data, this is what we have to do next step. We could have more prediction or like more accurate result where is exactly the location for the sensor. So we could use the location based on our computing, not from the ones that the volunteering or the people who have these sensors, they shared the information from them. So I talk about also how the sensor patterns affect on the accuracy. So as an example here, we observed that the aircraft crossing from sensor or from source to destination crossing different sensors. So if at time 1, it's received by sensor 1 and 2, and then at time 2, just only sensor 2, and then at time 3, it's received by another set of sensors. This is an indication that the aircraft was in the area of that sensor. And by moving on, it can like enter another area of another sensor, or it could be also leaving another area of the sensor. So from the experiment, we have this example, like different trajectory over time, and see how is the, let's say for the first figure there, how is like the sensors comes and appears in their trajectory. As an example, the 248 sensor, it was not appear in the trajectory and then started to getting to the sensor. So this means like it started to be in the area of that sensor. So this is an indication for us to have to consider to improve the accuracy of a prediction and to make like another parameter to predict the location inside the intersection area. For evaluation, we use 2 methods. The first method is the French distance. So basically, French distance, it's comparing if the 2 curves, which here in 2 trajectory, they are similar to each other or not. 0 means they are identical, and it goes up to, like, there's no up maximum for the French distance, but it depends on the application. In our scenario, we tested 2 trajectory from 2 different like aircraft, and it was up to 17 coupling measurements. So for method 1, we observed or we got by 0.8 coupling measurement. For method 2, it was improved by 0.4 coupling measurement. Still, they are okay, but still not nice. We have to improve this accuracy to make the prediction much perfect for like prediction the attack or detection the attack. Plus, the second method for evaluation, we use the standard deviation between the received location and the computed location for the whole point over the trajectories. Now the result, they are not that too much, don't be shocked, but like for the method 1, like the average is 20 kilometers, for method 2 is almost the same, 90 kilometers, but as I said, like we are going now to optimize the prediction. So so this is what we are done actually for so far, getting the sensor coverage, getting the location for the sensors, also predict the expected location based on 2 methods, analyze the result. But still we have to do like optimize the prediction by involving the sensor density, sequence of the sensors, also receive signal strength and trajectory length, and different parameters to improve the accuracy, and then use it for attack detection. Thank you so much. This is the conclusion. Like as we said, like ADSB has different its potential for a spoofing attack, and we have to deal with the spoofing attack. So different techniques are exist in the literature, but the point is how to get the new method to deal with the challenging with the existing method. So we propose like now an idea for based on the location of the sensors on the ground. And we're trying to optimize this method based on different parameters. So it's an ongoing process project. It's not done yet. So hopefully like we can get a nice result to predict the attacks. Thank you so much. And you're welcome to any questions.
Thank you very much. Questions? Okay, well, I promised during lunch that I have some difficult questions for you. Okay, so I'll start. Please join in. So can you maybe clarify a little bit what threat model you assume? So do you assume there is a legitimate aircraft in the air and now the attacker is injecting from the ground, trying to drift it, or what exactly is the threat model here?
Okay, we have two types of threat model. The first one is like the attacker listening to the packets that are broadcasted from the messages and try to spoof or modify the received messages and then like feed the air traffic control system with the modified location. This could be like the spoofed location, could be a random location anywhere, or it could be for the smarter attacker. He was precise and he was drifting the aircraft slowly, like from the legitimate air trajectory to make it like going to somewhere else. Yeah.
Okay, but there is certain assumption that attacker is also able to suppress all the legitimate ADSB messages, or otherwise you would have a little bit kind of mixture of the spoofed and legitimate ones, or not?
Yeah, they have to listen to the messages.
Yeah.
They have to. He can modify the messages.
He can modify it arbitrarily.
Yeah, sure, definitely.
Right,
yeah.
You
could also insert new messages. This could be also new insertion messages to ADSB messages. Yes, we believe that the messages are plain text, so they can modify it.
Okay. Yeah. All right. Thank you very much.
Thank you.
Any other questions? One more question here.
Hi, thank you so much for your presentation. I was just wondering, I believe in 2019, people that have been longer with Open Sky, correct me, but there was a Kaggle data challenge that also did exactly this of like predicting the location of the aircraft by the like sensor information. Have you looked into this? And how do you think you improve this, or what is the difference to what was done there?
Yeah, we were participating in this competition, to be honest. The point is most of the like solution from the competition, they were based on machine learning process. So in this way, we are trying to deal with that in a classical way without machine learning process. So I'm not dealing with machine learning. So try to find another way that could be easy, that could be not costly, and it also like how we could deal with other methods like intersection area. If there is a potential of getting like accurate result for predicting the location from the intersection area. So still like we have to analyze all these parameters to see the effect and the value of this method compared to the other methods actually. Yeah.
Okay, and you prefer not to use AI to avoid this black box approach because of security, or?
I don't have a preference not to use that because I'm working and I'm a lady working in a like classical way to predict the location. Even on our work, Map Pro, we were not taking like machine learning as a tool to predict the location. We just used like a classical way, the physics, how we could like based on the movement of the aircraft, how we could predict the location. It's all like all the method, they have pros and cons. So we have to deal with the prediction in a different way, not machine learning. So I'm taking care of this one. Yeah.
Okay. Yeah. Thank you so much.
My pleasure.
Okay. Thank you. Any more questions? Okay. If not, then let's thank the speaker again one more time.
Thank you.